Hello everyone, welcome to the week 11 of this course. So in this week we will even delve deeper into the large language models. We'll start this lecture by talking about scaling logic, that when you train large language models, how do you scale the performance? Like what do you focus more on? Do you focus more on the model size or do you focus more on the data set? So what does the literature say about that? So that's what will the focus of this lecture, and then we will move on to different variations in architectures than what we have already studied in this course. So we'll talk about two particular papers. So one was the scaling laws proposed by Kaplan et al. From OpenAI 2020, and second one was the one proposed by Hoffman et al. In 2022. Right? So Google DeepMind. So what do we mean by scaling laws of LLMs? So it's about when you say the performance of LLM, that's determined by three factors. One is what is the model size. Now what do I mean by model size? You can see the number of parameters, and let's say we exclude the embeddings. That will the first paper's view. So we exclude embeddings. Apart from that, we have the model size, and we have learned how to compute the model size, right, for encoder, decoder models. So let's say right now we are only focusing on decoder only models. So we have learned this n is roughly 12 times d model square times number of layers. That is the number of parameters that a model has. So it can be determined easily by what is the dimension, model dimension you want to keep, and what is the number of layers you want to keep, and this will tell you what is the number of parameters roughly. Right? You may have some changes in design, like you can do grouped query attention and all. It will change. Then it depends on how much data set has been trained on and how much compute you have used, because data set, how many steps you have gone will determine how much compute do you really need for that. So three things: model size, data set size, and how much compute has been used. So data set typically is denoted by the number of tokens that you are using. So you can see number of tokens that are used, and amount of compute. The way it is typically mentioned is in terms of PFTage, petaflop per day. What does it mean? So one petaflop day is doing 10 to the power 15, one petaflop neural net operations. So that many operations per second for one day, right? So this is 10 to the 15 into 24 into 60 into 60. And this gives you roughly 8.6 into 10 to the 19 flops, and this is roughly 10 to the 20. So if you do 10 to the 20 operations, that is one PFT. Okay. Now just to give an idea, let's say you have an 800 GPU, so it can do 312 teraflops, right? So this is 3 times 10 to the 14 flops, and this is roughly, yeah, so this is per second. So this is roughly 2.7 to the power times 10 to the 19 flops per day. So that means if you have 3 hundreds and you use them for an entire day, that's your one PFT. Right? One PFT is roughly equivalent to 3 800s running for a day. Right? So that gives you an idea that when we compare in terms of compute. So one PFT will need say 3 800s roughly for a day. Now let's take two example models, like just to get an idea like what kind of sizes and all they use. Like GPT-3, in terms of model parameters, they had 175 billion parameters. Number of tokens, they were trained on 300 billion tokens, right? And how many days? So you don't have the compute estimate, but you say okay, roughly 10,000 V100 GPUs were used 1 month of training. So yeah, you may try to compute the petaflops on there. Now this was 2020 model, and now if you see Llama model 2023, it's a smaller model, 65 billion parameters, but it has been trained on more number of parameters. So 1.4 trillion tokens, right? More, roughly 4-5 times that of GPT-3, and it used 2048 800 GPUs, 21 days of training. So maybe you can say 21 days of training divided by 3, for because 3 800 will be 1 petaflop into 2048. Roughly that may be that many PF days, you can say, right? That many PF days for Llama in terms of compute. Okay. So now the question is, if I have compute, where should I spend it? Should I spend it on increasing the model size, or should I spend it on increasing my data set size? Right? Like you see, the data set size is less, but data set size is more from GPT-3 to Llama, but the model size is smaller. Right? So is that more optimal? Right? What is more optimal if you have a certain amount of compute budget? So that's what I mean. This paper typically tries to answer. So would you train, for example, a 5 million parameter language model on 100 books, or I will train 500 million parameter model on a single book, or a 100K parameter model on 5K books, assuming they all, so in terms of multiplication, so you see they need roughly the same compute, right? How should I do my training? That's the idea. So this paper, this is the Kaplan et al. Paper 2020. So this gave the scaling laws for new language models, very commonly cited paper around scaling laws. So what they found, that they computed the language modeling performance, the test loss. So if it decreases, that's better. So it improves very smoothly as you increase the model size, right? So model size parameters you are increasing, the performance is going up, loss is going down. Same thing happened with data set size, right? And also the amount of compute used for training. So that means all of these are important. So if you increase data set size, parameters, compute, everywhere you will improve your loss. And you see the behavior is very similar. It's power law behavior everywhere, right? So that was one thing that they found. All three factors must be scaled and up in tandem, right? So you should scale them in tandem, and that's what will give you the best performance. Now, what more than that they could mention? Okay. So this was one thing. Performance depends strongly on scale. So model parameters, data size, and the compute used for training, but it depends very weakly on the model shape, like the depth and the width of the network that do not matter so much once you decide on the model parameters. And you model performance versus scale through power laws. Now it will improve the most if the model size and data set size are scaled up together, right? And say if you increase model size but you do not increase data set in tandem, you will have diminishing returns, right? So that's the thing that they said. You are increasing your model size, you also increase your data set size with that. How much we will see, like should I increase, if I increase the model size by 2, should I also increase my data set size by 2? So we'll see what do they say about that. And very interestingly, they say a larger model is more sample efficient than smaller model. Okay, so that means a larger model will take less number of steps to reach the same loss that a smaller model is using. So large models are more sample efficient than the small models. They can reach the same level of performance with fewer optimization steps. So here you have the number of tokens that have been processed, right? So this is actual data set size, and the yellowish one is the large parameter, so 10 to the 9 parameters, and this is low parameters. And what you are seeing, let's say I fix a loss, say this 4. So this is reaching it here, right? And this is never reaching it, and suppose something like that is reaching it in this much data set size. So larger models require much smaller data, right? So that means the compute you can divide, you may give more, you can give more compute to the model size than what you are giving to the data set size, is what this suggests. Okay. So this is one interesting finding. Then this is again a very similar plot that they do, that this is like 708 million parameter model, this is 708 million parameter model, this is 393k parameter model, and you increase the token in data set for the same loss, this achieves it in much smaller data set size than something like these models, right. So how many steps do you need? Again, these are very small number of steps that you need for the large models compared to what you need for the small models. So they are more sample efficient is what they suggest. Now this is very interesting, this particular diagram that they had. So this is like, as you have more compute available, how do you allocate it towards training large models? So you can do three things. So here you are going from compute of say 10 to the minus 8 to 10 to the power 1 PFtage. So it's order of a billion increase, right? So increase by a billion. So if you increase compute by a billion times, so you can increase three things: your model size, batch size, and number of steps, right? So batch size into number of steps will be your data set, right? So you have batch size into number of steps, and that determines your data set, number of tokens, right? And then you have the model size parameters. And compute is proportional to these. So compute is parameters times batch size times steps. Why? We will just briefly see in the next slide. So you want to distribute it here. So should I distribute equally among this? So if I have 10 to the power 9 increase in compute, should I give 10 to the 4.5 increase in parameters and 10 to the 4.5 in data set? That's not what they said. They said, okay, so increase should go more towards model size. So roughly like you increase your parameters by 10 to the 6 and data set by 10 to the power 3, and this you can distribute like batch size should be increased more. So 100 to batch size and 10 to steps. So this is what they are finding, right? So most of the data can be used to increase parallelism through larger batch size. So that's what they said. So if you have you want to increase data, you can use larger batch size. That will be helpful. Okay, and very small increase in the serial training time required. Okay, so and they give a nice estimate, that is the compute needed is 6 times NBS. N is the number of parameters, B is the batch size, and S is the number of steps. So batch size into steps is number of tokens. So that means every token you have roughly 6n computations, 6n flops per token. Six n flops per token. And what is the number of parameters? That means for every parameter you have every token you have 6n flops. So every token roughly passes through each parameter, and then you have 6 times that, and this includes both forward and backward. Now how do they come to that estimate? So they said, okay, let's take a typical transformer model. You have, and let's not worry about the embedding operations. So in embedding you have vocabulary and the context length. So this is your context size overall, right? This is for the positional index, positional embedding. So you see your embedding dimension will be vocabulary size times the model size, model dimension, right? And the position embedding will be context length times model dimension. Right? Makes sense. Then for attention, so I'll just talk from here. Attention, you have 3 matrices, query, key, and value. So for each layer you have the model dimension into attention, and this includes all the heads. So this will actually be same as demodel if it includes all the heads, right? Because otherwise this is demodel by H, and then you have H attention heads. So you have roughly, this is also, the attention is also demodel. And then they say how many flops you will take per token during forward pass is twice these parameters, 2 times n layer demodel 3D attention. Okay, so they say in forward pass per parameter you need 2 flops. Similarly, they say for projection in attention. So, you have this WO matrix that has d square parameters, right, into number of layers. So, you have again 2 flops per token. In feed forward, you have a feed forward dimension. So, it is d model into d for feed forward, and again d for feed forward times d model. So, 2 times d model times DFF, and you need twice of that. And then d embedding again will have some flops. So, if you add all these, you get let us focus on these main things, this, and this. How much is this? So, this is 2 into 3, 6 times d model square into L. This is 2 times d model square into L, and this is 2 into 2, 4, and DFF is 4 times. So, 16. So, if you add all this, you get 24 times d model square into L. Now, what is that? Remember, what is the number of parameters? 12 times d square model into L. Right? So, this is just twice of that. So, this is 2n. Plus, you have some other operations, and this they count as this. And this will be smaller if this n context length is if d model is much larger than n context by 12, right? You can see this. So, if it is generally context length is not 12 times model dimension, right? So, this is okay, reasonable assumption. So, this becomes a smaller term in this, and you can just focus on this 2n as the main cost. So, that makes it very easy. So, per parameter you have 2 flops in the feed forward and in the forward pass, and then when you do backward pass you need 4 flops per parameter. So, together you have 6n floating point operations per turning token, right? That is what you do. Now, why do they talk about 2 operations in the feed for per token? I mean, just to give you an idea. So, let us think about one weight. So, it will connect 2 units. So, you need 2 operations, one when you multiply HI with W, and second, so one is for multiplication, and then flop 2 will be needed because AJ will add this multiplication output to its current output, right, because it is getting it from here. So, it already have some output, plus it will add this particular output. The second will be add, right. So, you will the unit I will multiply its output by W to send it to unit J, and the unit J will add this contribution to its total input. So, you had 2 operations, 2 floating point operations per weight. And similarly, you can see in this blog you have other ideas that why you have another 4 flops during backpropagation, right. So, that is how we get to this 6n. Now, 6n that means is only for per token, and then you have batch size, that many tokens into is that many steps. So, 6n BS is a good estimate for how much compute you will need for training for certain batch size times certain number of steps. Okay. Right. Now, this was a very interesting paper and lot of interesting figures, but there were certain issues that people pointed out with these laws. Like, for example, they use the same learning rate schedule for all the training runs, regardless of how many training tokens or batches they were using. But ideally, people do schedulers. You adjust this learning rates, so it can change the performance. So, people said they are little bit flawed because of this, and later on, Chinchilla in DeepMind paper, so they came up with a new scaling laws. This is training compute optimal large language models. So, this paper again is very popular, which gave which again refined the scaling laws. So, quick takeaways. What is the difference between the laws given by Kaplan versus Hoffman? So, Kaplan, for example, we saw that if you are able to increase your compute budget, you should prioritize increasing model size, right, than your data set. So, if you have a 10x compute increase, you should give 5 to data to the model and 2 to data. If you have 100 times compute increase, give 25 to model, 4 to data. So, give more to the model. While Hoffman said you should increase model and data set at the same rate. So, if you have 10 times compute increase, you increase both model and data by 3.1 times, and 100 times you increase both by 10 times. So, they said that you increase both by the same rate. Okay. And they actually saw some examples. So, they compared with some of these models like Lambda up to Gopher and all. So what was their size and what are the number of parameters versus what are they trying to build in Chinchilla. So 70 billion parameters and 1.4 trillion training tokens. Okay, and then their analysis reveals that a compute optimal model should use roughly 20 tokens per parameter. So every parameter you should use 20 tokens, and so that's what they used in their model. So 70 billion parameters, 1.4 trillion tokens, and this as per this estimation, some of the recent models are actually like very overtrained. Like if you see Llama 3 70 billion, it uses 14 trillion tokens. That's 200 tokens per parameter. Like this is 10 times what Chinchilla had suggested. Like 5.3 same, it is 875 tokens per parameter, and Llama 3 1875 tokens per parameter, 8 billion model. So they are slightly overtrained by this definition, but that's what Chinchilla mentions. So our NLP book, so this chapter 10 gives some idea about these scaling laws also, right? And you can read through these papers to learn about these in more details. So we will continue discussing about various architectures and the differences from what we have learned from the next lecture. Thank you.